The central limit theory stands as one of the most fundamental and powerful results in the field of modern statistics and probability theory. Its profound implication that probabilistic and statistical methods designed for normal distributions can be applied to a vast array of problems involving other types of distributions has made it an indispensable tool across numerous disciplines from engineering and biology to economics and finance. The theorem provides a theoretical bridge that connects the often complex and unknown probability distributions of individual variables in a population to the predictable, well understood properties of the normal or Gaussian distributions. This connection is established not by examining the individual variables themselves, but by studying the behavior of their sample means. In finance, this theorem has been leveraged to provide a theoretical justification for the widespread assumption that asset returns, particularly over long periods or within diversified portfolios, can be modeled using a normal distribution. However, this application resets on the set of critical assumptions that are often tenuous in the context of real-world financial markets. The core concept of central limit theory can be understood through a simple intuitive process. The theorem states that for a given population with underlying probability distribution, the distribution of the means of the sample drawn from the population will approximate a normal distribution, provided the sample size is sufficiently large. This holds true regardless of whether the original population's distribution is uniform, skewed, binomial, or any other shape. A classical illustration of this principle is the rolling of a dice. A single die has a discrete uniform distribution. The probability of rolling any number from 1 to 6 is equal at 1 by 6. If one were to roll a single die 1,000 times and plotting the result of each outcome, the resultant histogram would be flat. Now consider taking a sample size of 2, meaning we'll be considering 2 dice and calculating their average. The distribution of these averages is no longer uniform. An average of 1 or average of 6 is far likely than an average near the center, such as 3.5. For instance, an average of 1 can be achieved one way, 1 plus 1 by 2, with a probability of 1 by 6 into 1 by 6, which will be equal to 1 by 36. In contrast, a central value is more probable because numerous combinations of rules can produce it. As the sample size increases, for example, by averaging the outcome of 3, 5, or 10, this effect becomes more pronounced. The distribution of the sample averages becomes progressively smoother and more bell-shaped, rapidly converging towards a normal distribution. With each additional die, the probability of achieving an extreme average diminishes exponentially, while the probability of achieving an average near the population mean of 3.5 or something increases, tightening the distribution around this central point. Formally, the Lindbergh-Levy version of central limit theory provides the mathematical foundation for this observed convergence. Let x1, x2, x3, and so on till xn be a sequence of independent and identically distributed random variables, each with a finite expected mean, mu, and a finite non-zero variance, sigma square. Now, the sample mean of this sequence of random variables will be xn is equals to x1 plus x2 plus so on till xn by n. The theorem states that as the sample size n approaches infinity, the distribution of the standardized mean given by the random variable zn converges to the standard normal distribution with a mean of 0 and a variance of 1. Now zn can be written like this, where xn is the sample mean, and u is the expected value or expected mean, and sigma is the standard deviation of the population, and n is the number of samples taken. So zn is equals to mean of xn minus u by sigma by root n. Here, d denotes convergence in the distribution. This means that for a large enough sample size of n, the distribution of the sample mean xn can be well approximated by a normal distribution with a mean equal to the population mean and a variance of sigma squared by n. The term sigma by n is known as a standard error of the mean, and it quantifies the dispersion of the sample means around the true population mean. As n increases, the standard error decreases, indicating that the sampling distribution becomes more tightly centered around mu. The immense utility of the theorem lies in this result. It allows for the application of statistical techniques and hypothesis tests that rely on the normal assumption, such as t-test and z-test, even when the underlying data is not normally distributed, provided the sample size is inadequate. Now, let us look at a small example. Suppose we have a population of exam scores, assuming that the population is a skewed distribution with a expected mean of 70 and expected deviation of 10. Now, if we take 40 random samples of size 30, and calculate the means of each sample, the means will be approximately normally distributed. The center 70, the standard deviation of 10 by root 30. Now the z-score for this will be sample mean minus 70 by 10 by root 30. So this is one way of leveraging this formula. The powerful conclusion of the central limit theorem is conditional upon a set of strict assumptions. The validity of applying the theorem hinges entirely on whether these conditions are met in practice. The failure to respect these assumptions is the primary source of the theorem's misuse in financial modeling. First and foremost, the classical CLT requires the random variables in the sample to be independent and identically distributed. Identically distributed means that every observation is drawn from the same underlying probability distribution with the same mean and variance. Independent means that the value of one observation provides no information about the value of another observation. The second assumption states that the theorem requires a sufficiently large sample size for the approximation to normality to be valid. A common rule of thumb in statistics is that a sample size of n greater than 30 is generally sufficient for CLT to apply. However, this is heuristic and not a mathematical law. The actual sample size required depends heavily on the shape of the underlying population distribution. Now, the third assumption is that CLT assumes that the population from which samples are drawn has a finite variance. This mathematical condition is crucial because it implies that extremely large deviations from the mean are not just rare, but are constrained in a way that allows for a well-defined measure of dispersion. If the population variance is infinite, as is the case for certain types of fat-tailed distributions, the CLT in its classical form does not hold. This assumption is particularly problematic in finance, where empirical evidence strongly suggests that the distributions of asset returns exhibit fat tails, meaning that extreme events occur far more frequently than a normal distribution with finite variance. The potential for infinite variance in financial data directly challenges the applicability of the CLT and the models built upon it. It is important to distinguish the central limit theorem from another fundamental theorem of probability, the law of large numbers, as they are often in conjunction but describe different aspects of the sampling process. The law of large numbers describes the convergence of the sample means value. It states that as the sample size n increases, the sample mean xn will converge in probability to the true population mean u. In similar terms, the LLN tells us that with enough data, our sample average will become an increasingly accurate estimate of the true average. It answers the question, where is the sample mean going? The central limit theorem, in contrast, describes the distributional form of sample's mean and fluctuations around the population mean during this convergence process. It does not focus on the value of a single sample mean, but rather on the shape of the probability distribution found by many hypothetical sample means. The CLT tells us that the distribution of these sample means will be approximately normal. It answers the question, how does the sample mean vary around its destination? In summary, LLN guarantees that the sample mean will eventually be equal to the population mean, while CLT describes the bell-shaped pattern of errors or deviations we can expect to see in our sample means along the way. The central limit theorem provides a powerful theoretical license for financial modelers to assume normality. This assumption simplifies the immensely complex and often chaotic behavior of financial markets into a tractable and elegant mathematical framework. By viewing long-term returns as the sum of many small independent increments, or portfolio returns as the sum of many individual asset returns, the CLT is invoked to justify the use of normal distribution. This idealized world, where risk is synonymous with the standard deviation and return are neatly bell-shaped, forms the bedrock of many of the most influential models in modern quantitative finance, including the modern portfolio theory, value at risk, and the Black-Scholes-Merton option pricing model. So, the first application of CLT we'll be looking at is modeling aggregate portfolio returns over time. This is a foundational application of CLT in finance. The logic proceeds as follows. A total return over a period, such as a year, can be conceptualized as the sum or average of a series of shorter term returns, such as daily or weekly returns. If one assumes that these short-term returns are independent and identically distributed random variables, then the CLT directly implies that the sum or average will tend towards a normal distribution as the number of periods increases. This provides a theoretical rationale for why, even if daily returns follow some complex non-normal distribution, the distribution of annual returns might be reasonably approximated by a normal curve. The next application we will see is the application of CLT in modern portfolio theory. Modern portfolio theory, pioneered by Harry Markowitz, provides a mathematical framework for constructing portfolios that optimize the trade-off between risk and return. The theory's central tenet is that an asset should not be evaluated solely on its own characteristics, but on how it contributes to the overall risk and return of a portfolio. MPT fundamentally assumes that investment returns can be adequately described by two key parameters, the mean and the variance. The assumption that portfolio returns are normally distributed is the key element that makes MPT framework mathematically tractable and elegant. The normal distribution is completely described by its first two moments, the mean and the variance. Therefore, if the returns are normal, an investor's entire decision-making process can be reduced to a two-dimensional problem, maximizing the mean return for a given level of variance or minimizing the variance for a target level of return. return. The CLT provides the theoretical justification for this normality assumption for diversified portfolios, thereby simplifying the complex multidimensional problem of asset allocation into a manageable optimization exercise. Next, we will see the application of CLT in risk management via a pragmatic approach to value at risk. Value at risk, or VAR, has been a standard tool in financial risk management for quantifying the potential loss on a portfolio over a specified time horizon at a given confidence level. For example, a 1 day 99% VAR of 1 million signifies that there is a 1% chance of the portfolio losing more than 1 million over the next trading day under normal conditions of the market. There are several methods for calculating VAR, but one of the most common is the variance covariance method, also known as the parametric or delta normal method. This approach explicitly and fundamentally assumes that the portfolio's returns are log normally distributed. The theoretical justification of this assumption is once again the CLT theorem applied to a large diversified portfolio. Under the normal assumption, the VAR calculation becomes remarkably simple. The potential loss is expressed as a multiple of the portfolio standard deviation. The multiple of z-score is determined directly from the properties of the standard normal distribution and corresponds to the desired confidence level. For instance, at a 95% confidence level, the z-score is approximately 1.65, and the 99% confidence level, it is approximately 2.33. The formula is often represented as VAR is equals to U plus Z into sigma, where U is the expected return, Z is the z-score for the given confidence level, and sigma is the standard deviation of the portfolio's return. The central limit theorem, by justifying the use of normal distribution, enables this straightforward analytical approach to risk quantification, which is widely used by financial institutions for risk reporting and capital adequacy calculations. At last, let's look at the application of central limit theory into pricing derivatives, like the Black-Scholes-Merton model. The Black-Scholes-Merton model, a cornerstone of modern option pricing, also relies on the foundational assumption rooted in the logic of CLT. The model does not assume that the stock prices are normally distributed. Such an assumption would be flawed, as it would imply a non-zero probability of negative stock prices, which is impossible due to limited liability. Instead, the BSM model assumes that the continuously compounded returns of the underlying asset are normally distributed. This assumption implies that the stock price itself follows a log normal distribution. A log normal process is one in which the logarithm of the variable is normally distributed. This is a more realistic model for asset prices, as it is bounded by zero on the downside but has unlimited upside potential. The theoretical justification for this assumption is an extension of CLT to a continuous time framework. The model posits that the stock price follows a geometric Brownian motion, which is essentially a continuous time random walk. The price at any future time is the cumulative result of vast number of infinitesimally small random price changes. The aggregation of these continuous random increments by the logic of CLT leads to a normal distribution of the cumulative log return, and thus a log normal distribution for the final stock price. The financial models discussed now do not operate in isolation. They form a deeply interconnected analytical ecosystem with the central limit theory and the resulting normality assumption serving as the common foundation. This interconnectedness creates a powerful but fragile chain of logic, where the failure of the core assumption in one area can have severe cascading effects on the others. The process often begins with the modern portfolio theory, which uses the normality assumption to construct an optimal portfolio based solely on the mean and variance. Risk managers then take this portfolio, which is only optimal within the idealized normal world, and apply a value at risk model, also assuming normality. To quantify and manage its risk concurrently, traders and structurers might use Black-Scholes-Merton model, which relies on related log normal assumption to price and hedge options on the very assets contained within that portfolio. This creates a systematic vulnerability. A fundamental breakdown of the normality assumption does not just invalidate a single model in isolation. It compromises the entire framework. If MPT produces a portfolio that is dangerously suboptimal in real, non-normal world, the VAR models will systematically understate its true risk, providing a false sense of security. At the same time, the options used to hedge this misspecified risk will themselves be mispriced by the BSM model, potentially rendering the hedges ineffective precisely when they are needed the most. This chain of dependence means that the entire risk management and investment apparatus can fail in union, as the same foundational law permeates every link. The idealized world of finance, built upon the elegant simplifications afforded by the central limit theory, stands in stark contrast to the empirical realities of market behavior. While the assumption of normality is mathematically convenient, extensive analysis of historical financial data reveals that it is a poor descriptor of how asset returns actually behave. The critical assumption of the CLT, namely that observations are independent and drawn from a population with finite variance, are systematically and profoundly violated in financial markets. Two key empirical phenomena, volatility clustering and the prevalence of fat tails, directly contradict these assumptions. Their existence means that the models based on the normal distribution are not just imprecise, they are fundamentally misspecified, leading to a dangerous and systematic underestimation of risk, particularly the risk of extreme events. Now, first, let's look into what volatility clustering is. It is one of the most well documented facts in financial econometrics. It is the empirical observation that large changes tend to be followed by large changes of either sign, and small changes tend to be followed by small changes. In simpler terms, market volatility is not constant over time. Instead, it clusters into distinct periods. Turbulent high volatility periods tend to persist for some time, just as calm low volatility periods do. This behavior is visible across virtually all financial time series, from individual stock prices to exchange rates and market indices. This persistent clustering behavior of volatility directly violates the crucial independence assumption of the central limit theorem. The IID condition requires that each data point is an independent draw from a stable probability distribution. Volatility clustering demonstrates that that is not the case. The magnitude of today's price change is not independent of the magnitude of yesterday's price change. While the returns themselves may show little no contribution, their absolute values or the squares exhibit a positive, significant, and slowly decaying autocorrelation function. This means that the variance of return process is time dependent and predictable to some extent, a feature that has led to the development of models like ARC and CARC. Now let's look at the second major empirical deviation from normality, which is the presence of fat tails in the distribution of asset returns. A distribution with fat tails is one that has higher peak and fatter tails than a normal distribution. This means that extreme events, both large gains and large losses, occur far more frequently in reality than a normal distribution would predict. A normal distribution has thin tails, meaning the probability of an observation decays exponentially as it moves away from the mean. Events that are more than 3 standard deviations from the mean are exceedingly rare, with a theoretical probability of about 0.3%. Events of 5 or 7 standard deviations are considered statistically impossible. However, the historic record of financial markets is littered with such impossible events. From the stock market crash of 1987 to the 2008 financial crisis and the 2010 flash crash, the actual distribution of market returns consistently shows that the frequency and magnitude of severe downside periods are significantly higher than investors might expect based on a normal distribution model. This existence of fat tails directly challenges the CLT's assumption of a finite and well-behaved variance. Some theoretical distributions propose to model these fat tails, such as the stable Parisian distributions advocated by Mandelbrot, possesses infinite variance. If the true underlying distribution of the returns has infinite variance, the central limit theorem is not applicable in its classical form. Even if variance is technically finite, the presence of leptokurtosis means that we'll systematically understate the true probability of extreme outcomes. The combined effect of volatility clustering and fat tails is that financial models built on the foundation of CLT and normal distributions are inherently misspecified. This may provide a passable description of the market behavior during normal, tranquil periods, but they fail catastrophically when robust risk management is most critical during the periods of market stress and crisis. This leads to a dangerous and systematic underestimation of tail risk, the risk of an investment moving more than 3 standard deviations from its mean, resulting in extreme losses. Models based on the normal distribution assign vanishingly small probabilities to such events. This discrepancy is not a minor calibration error, it is a fundamental flaw in the model's conception of reality. By assuming away the true nature of the risk in financial markets, these models create a false sense of security, encouraging institutions to take an excessive leverage and leaving them dangerously exposed to risky events that the models themselves deemed impossible. Ultimately, the role of central limit theory in finance is a cautionary tale. It is a tool of immense theoretical power, but its utility is bounded by the validity of its assumptions. A prudent and effective approach to financial modeling requires moving beyond the seductive simplicity of the bell curve. It demands deep respect for the empirical data, a critical awareness of model limitations, and the adoption of more robust frameworks that acknowledge the true non-normal nature of risk in financial markets. The future of risk management and financial stability may well depend on the ability of practitioners to look beyond the idealized world of the CLT, confront the complex realities of the markets they seek to model.